All right, let's just jump right in. We're going to prove today that calculus isn't just a bunch of arbitrary, confusing symbols on a chalkboard. It is literally the engine powering our modern world. I know, when a lot of us hear the word calculus, we instantly picture these incredibly complicated equations that feel totally disconnected from real life. But honestly, calculus is really just the mathematics of change and motion. That's it. And in this explainer, we're going to demystify one of its two massive pillars, the integral. Stick with me, because by the end of this, you're going to see exactly how this single mathematical concept is quietly running pretty much everything around you. So why do we even need this math in the first place? Well, let's look at the core visual problem. If I ask you to find the area of a perfect rectangle, you already know the answer, right? Super easy. You just multiply the length by the width. Done. But the real world is rarely made of perfect straight lines. What happens if the shape you need to measure has a curvy, completely irregular top? Suddenly, your simple straight line formula completely falls apart. You literally can't just slap a ruler on it and call it a day. This was a massive, huge roadblock in early mathematics. How do you accurately measure the chaotic, curvy realities of our physical world? And here is the absolute genius solution. To find the total accumulation, which is just the area under that crazy irregular curve, you divide the whole thing up into rectangles. But wait, not just a few rectangles, you divide it into an infinite number of ultra-thin vertical rectangles. Since each tiny little sliver is so impossibly thin, its top is basically flat. So by calculating the area of all these infinitely thin pieces and then adding them all together, you get the exact total area. Boom! That right there, that's the heart of an integral. It is the ultimate mathematical tool for finding the exact total accumulation of, well, anything. Which brings us to section 1, clearing up the jargon. Before we get into all the wild ways this is used today, I want to make sure the core concept doesn't get buried under intimidating math vocab. It is so easy to fall into a trap here because the terminology sounds almost exactly the same, but we are looking at two entirely different mathematical concepts. Over on the left, we've got integral numbers. Now, in basic arithmetic, that's really just a fancy way of saying integers. You know, whole numbers with no fractions or decimals, like -3, 0, or 5. But on the right side, we have the calculus integral. This is the advanced operation we're actually digging into today. It's symbolized by that tall, continuous line, and it's used to calculate accumulation, areas, and volumes. So just to be crystal clear, whenever we say integrals in this explainer, we are strictly talking about the right side of the screen. Moving right along to section 2, two sides of calculus. To really get how this fits into the broader mathematical family, you have to realize that calculus basically acts as a two-way street. The crucial thing to understand is the fundamental theorem of calculus. It splits the whole field into two main branches that act as perfect inverse operations. They are just like addition and subtraction. On the left, we have differential calculus, which deals with derivatives. This is the math of taking something complex and breaking it down into microscopic pieces to find a precise rate of change. Think of it like taking a massive road trip and using a derivative to find out exactly how fast you were driving at exactly second 42 of the journey. Then, on the right, we have integral calculus. Integrals do the exact opposite. They take your constantly changing speed from every single second, join all those tiny pieces back together, and calculate the exact total distance you traveled, pulling apart and putting together. Honestly, if you take the integral of a function and then take its derivative, you end up right back exactly where you started. How cool is that? Let's look at the history in section 3, a 17th century math rivalry. You know, math wasn't just handed down on stone tablets. It actually has this incredibly rich, dramatic human history filled with fierce rivalries. The conceptual roots of the integral stretch all the way back to ancient Greece, around 250 BC. The brilliant Archimedes used something he called the method of exhaustion to find the area of circles by cramming straight-edged polygons inside them. But the real game-changing breakthrough, that happened in the late 1600s, thanks to two rival geniuses. Over in England, Sir Isaac Newton invented the concept to solve complex problems in planetary motion, and he called it the science of fluxions. But right across the channel, the German mathematician Gottfried Wilhelm Leibniz developed the exact same concept completely independently. And actually, we have Leibniz to thank for the notation we still use today. You know that tall, elegant integration symbol? It's literally just an elongated S. It stands for summa, which is the Latin word for sum. Okay, on to section 4, integrals in the real world. All right, enough history. Let's leave those 17th century equations behind and zoom out. Let's look at the massive real-world big picture of what this math actually builds for us today. And we'll start with a super high-energy application, rocket science. Look, space exploration relies completely on integrals. When you launch a satellite, gravity isn't just one constant pull. It physically weakens the further that rocket gets from Earth. That means the force required to push the rocket upward is changing every single millisecond. You simply cannot use basic multiplication to figure that out. Instead, engineers use integration to sum up all those constantly shifting forces. That tells them the precise total energy and fuel required to actually get that rocket into orbit. But hey, integrals aren't just for physics. They are literally the backbone of modern finance. In the business world, market trends are these incredibly complex curves that represent shifting supply and demand. Economists use integrals to calculate the area right under those complex curves, which helps them determine two absolutely vital metrics, consumer surplus and producer surplus. By finding these total accumulations, businesses can perfectly price a product. They find their absolute maximum profit while still keeping the market running efficiently. It's a total game changer for economics. And get this, these applications are literally saving lives. When you go into the hospital for a CT scan or an MRI, the machine is snapping thousands of flat 2D X-ray slices of your body from practically every angle. But your doctors, they need a 3D model to actually see what's going on. So the machine uses this insanely complex mathematical process called the radon transform. Because it relies so heavily on integration, it can mathematically piece all those tiny 2D slices back together, accumulating them all to literally build a flawless 3D digital image of your internal organs. It's amazing. Now, if you're thinking integrals don't affect your daily downtime, think again. Every single song you stream on Spotify and every annoying background noise that gets blocked out by your noise-canceling headphones, yep, that all relies on advanced integration called Fourier transforms. This whole process takes raw, chaotic, continuous sound waves and integrates them, converting that messy audio into compressed, neat digital data like MP3s. Without integration, the portable digital music we all love today simply wouldn't exist. Finally, just take a look around your city, our physical infrastructure. Those beautiful, sweeping, curved bridges and massive arch stadiums, they stand strong purely because of this math. Because those shapes are curved, the weight distribution across the whole structure is incredibly irregular. So civil engineers rely on integrals to calculate the exact structural stress and find the precise center of gravity. Integration ensures that the total load is perfectly balanced, which means all that gorgeous architecture around us doesn't just instantly collapse under its own weight. So whether you're trying to find the total volume of an oddball, irregular object, tracking the exact total distance of an accelerating car, locating the center of mass on a brand new curved bridge, optimizing consumer surplus in the stock market, compressing digital audio, or running a 3D medical scan, the rule is remarkably simple. Whenever we need to find the total accumulation of a continuously changing thing, the calculus integral is the absolute ultimate indispensable tool. So we've seen how slicing a curvy shape into infinitely thin pieces literally gave us the keys to rockets, MRIs, and our entire digital world. The modern world as we know it is quite literally built on the mathematics of change, which means the question really isn't just about what calculus is anymore. Instead, the question is, now that you understand the mathematical engine running the world, what are you going to build with it?